My name is Lior. I don't know if you recall, I gave like a tutorial right at the beginning, and there was a break and a lot of other tutorials. So today we're going to talk about neural surface reconstruction, and this topic is really close to my heart because it's basically my field of research. So most of it's kind of like coincidence, but also not that the things that I will present will be some of my works. So whatever, feel free to ask questions. So just a short recap of what you talked about with Mirav. She started by introducing to you some inverse problems, and specifically, how can we use the prior of deep neural networks in order to kind of like solve some inverse problem, for example, doing super resolution or noise removal or artifacts such as JPEG. And this was like in the concept of the work that it's called deep image prior. Next, you started to shift from 2D to 3D, where we introduced the one of the major computer vision problem that is called structure for motion, when you're given a set of images of some area or object, you want to reconstruct the 3D structure, which can be the cameras and also some sparse reconstruction of this building. And from that, you kind of shifted to computer graphics, where the idea is to go from 3D to 2D. And you talked about rendering, and one of the seminal works that started this concept that it's called the rendering equation, which was like 40 years ago. And it was like introducing the concept of taking some synthetic 3D scene and capture it and render it, meaning transforming it to 2D in the most realistic way that is possible. So this looks pretty old, but that was like the first rendered picture that kind of, I don't know, started this field. And I guess we all know what is the capability of rendering today with Disney and all of, I don't know, the computer games that some of you may play. And from that, we kind of wanted to combine this two concepts and idea of inverse problem and using the prior of deep neural network and computer graphics. And you have been introduced with implicit neural representation, where the idea is to use a deep neural network and specifically a fully connected network in order to learn to present some 3D field or 3D function. So you can either represent a surface as a sign distance function that caption for each point in 3D the value, the sign distance function to the surface, or an indicator function. I like to kind of like differentiate between the both. As like the left is like regression problem, and this one is like classification, right? When you just need to indicate whether you're inside or outside. And in that way, the neural network will present us the surface is the zero level set of that function. For me, when I first introduced this concept, I found it very nice that I can clearly see the neural network that I'm training. I don't know if you can relate to this concept. By the way, any question? Feel free to ask. And last thing, this is very much the combination of the two last concepts of how can we use neural representation in order to render in a realistic way the scene that we are representing. And this concept is called neural rendering, and specifically you talked and introduced to a paper that is called neural radiance field, the NERF, and we'll do and maybe more dive into recap onto that, because we need to be based on that for the rest of the class. I know that maybe these topics can be some new, so again, feel free to ask some question, and if I need to hold on something, please let me know. So really in high level, and we can do that quick, the idea of neural radiance field, or in another abbreviation, it's called NERF, is to model the scene, again, using a neural network fully connected. or an MLP that can as input a 3D position and a viewing direction. And for each point and a view direction, it predicts the density, the amount of material like geometry that exhibits in that 3D position, and the color that is emitted from this position into the direction of the view direction. And using this scene representation, neural representation, you can render the scene using volume rendering. And the idea is that you need to describe how you render each pixel. So what you do, you just like shoot a ray through this pixel, sample a few points along that ray. For each point, you evaluate the function, and you can get the amount of the density and the color. And using volume rendering, where the idea behind volume rendering is just like go and find the expected color along the ray based on the density amount. And this will be your rendered color. And because all this process is differentiable, you can simply use a rendering loss, just like regression, and compare the predicted rendered color to the ground truth. So the base idea is to kind of like simulate the rendering in order to learn the representation given a set of cameras. Yes.
In here, we assume we have an implicit representation of the 3D model, or we assume we don't, or we like what do we want to do? We want to make the representation better, or just get new rendering?
So you're given with not like so at the beginning, you're just giving with a set of cameras and like a set of input views and their corresponding cameras. You don't have, you can initialize your neural representation whatsoever. Normally, you just like use a random initialization. And you basically want to, oh wait, I don't know why you say this. Okay. You basically, this is like a caption, like an image from the middle of the training. But at the beginning, you don't have nothing. But while you're training with a multiple views, you're eventually going to reconstruct the scene, and then you will be able to render it. Okay? Yes.
Can you repeat again? What exactly is the ground truth? How do you take the ground truth?
So, yeah, so the parameters are described here. Think that you're given a set of images and their corresponding cameras. This is the ground truth. This is your input. What is the output? Is a scene that you can render from all of the, like, you can interpolate between those cameras that you're viewing. Okay, is that clear? Sorry, so the task here is really, I mentioned it before, is novel view synthesis. You're given a set of cameras, but they're pretty dense, but again, they're not dense for each one because again, it's like infinite amount of cameras, and you want to make novel view synthesis, which you want to render it from views that you haven't seen in the scene. Okay, so this is the task here. Any question further for this? Yes.
In the beginning, when you're looking at the rays projected onto the 2D images, how do we, is the network learning the depth? Where does that, how does it know?
So it's not learning the depth. Oh, wait. Oh, no. Okay. It's not learning the depth, it's learning the density. So think of like, I don't know, this bottle, for example. You can think of your word as like R3, right, in 3D. And for each point, it can indicate high density or low density. Okay, so it doesn't matter, and you just query that on the rays. But eventually, it's in 3D, and you can capture it for like from any from any view. I don't know if I've confused you or
A little bit, but
yeah.
there in the leftmost image, we have,
Yes.
we're taking points along the array.
Yes, and then we.
But it's just a 2D image, so how do we?
No, the input is okay. The input that you have is the 2D image. How you use it, it's a different way from what you've been maybe used to knew before in this course. You don't input this image. You use this image in the camera parameter just to shoot the ray, right? You sample points in 3D along the ray, and then your input to the network is these points. It's just like 3 coordinates, X, Y, Z. You query these points, you get density. This will give you the amount of like how much geometry is lying in this point. you also get condition on the view direction, you're gonna get the color. So like this is your intermediate output. You get a camera, you shoot a ray, you don't use the image yet, you just have these points along the ray. Then, given all of these points, you can sum them up, and it's weighted by the density amount. Like if you have many density in these 3D points, like this point will not contribute to this integral. This point, because it's like hitting the surface, we're gonna give you the color that is like this orange one. Only now we're gonna use the input points as the ground truth, because you know that this point should be corresponding to the input ground truth image that is given to you.
The model still get the density.
Yeah, and the model just learned the density. Okay? Yes.
It's pixel wise or?
Yeah, it's pixel wise.
No, nothing get to.
Actually, you just when you train, like if you want to get into details, you random an image, you random some pixel out of it, like 1000 pixel, this is your badge, and then you do that iteratively. Yes. Okay, this is important, these questions, because this concept that is pretty new, we're gonna rely on that. It is just, I know it's like a different kind of like perspective of how you train neural networks. But think of it as like a function learning, right? You want to approximate some function, but here your function is an MLP. And that's it. Okay.
And the shadow that we see, it's just because
What?
with the shadow that we see while you turn around the tractor,
Yeah.
because we assume the model assume that it's the direction of the light is from where we took the initial camera.
Yeah, so think of that you have the supervision for multiple views.
Actually,
And because you have like supervision for multiple views and it's conditioned on the view direction, it learns how to model this function depending on the view direction, and like that, like modeling the specularities and the shadows and all of this. This is why it has like all this, it learns all this thing. Okay, so I'm continuing.
So
Yeah,
basically,
yes.
there is no input to the network. You're each time rendering to different view
Yes,
and checking and building the loss.
yes. You can think of it like it's related to what maybe we started it. This is done implicitly. The network learning using the rendering loss implicitly the same. Okay, this is where the name is coming from. Okay, so today we're gonna the paradigm of the learning will be kind of similar, but our goal is different. So we are still given as like input to the problem, not input to the network. Let's do this difference. And multi-view images and their corresponding camera parameters. We know how these images were captured in real life. And now our goal, I told you that the goal for NERF was to do novel view synthesis, meaning to render novel views that is not captured by these cameras. And today our goal is to do surface reconstruction. So we want to extract a dense 3D surface out of these images. Okay, and just to make sure, when you're gonna get the 3D surface reconstruction, you normally will get novel view synthesis, but it's not the other way around, and we're gonna see it now. So really the question is, okay, we have NERF. I told you that the density model the same geometry. Why can't we use that in order to do surface reconstruction? So the basic idea is because we model the geometry as a density, it's not really reliable. And if we're gonna take like some thresholds of the density of NERF, for example, as you see here, like threshold of all the points that for the density equals 50 or 500, we're gonna get a very, very noisy surface. And that is because this the density is very arbitrary, right? It doesn't have any localization of representing the surface, and it has like a lot of ambiguity that, and that is why we get this noisy surface. Yes.
This is from one vantage, but if you averaged over many.
No, so think that the output of what you learn is a 3D representation. Like for each 3 points, you have the density. So it doesn't depend on the view, right? So the density only depending on the 3D position. So it's not only from this view.
Function of the position and the viewing.
So yeah, it's kind of like a thing that I'm misleading you. The density is a function of the position, and the color is the function of the position and the color. Yeah, sorry.
What is the structure of the network? Basically,
Fully connected neural network. Linear layers. 8 linear layers. That's it.
We need more.
how many layers?
I think it's like normally it's like 8, but it's think of like, you know, if you, I don't know if you take or had this course, but you talk about the origin of talking about fully connected neural network is just like approximation of some functions, right? You don't need convolution or something like that. You just like need linear layer in order to represent the function. That's what like this kind of shift you maybe need to do. It's like we're not looking at networks like we done before. We're looking as network as functions, and that's it.
Can you go a
Yes.
slide back?
Of course.
No, one more.
This one?
One more. Where are the inputs and the outputs?
Yeah.
So the volume rendering,
Mhm.
there is a real representation of the 3D structure.
There's a what?
There is a real representation of the 3D structure, or only
Or only what? Sorry.
only 8 layers. I mean,
So the 8 layers are the representation of the function. Like
so when you're
this is the representation of the function. It's an NLP that the input is 3 coordinates and principally after also the view direction. And the output is 1 scalar for the density, 3 scalars for the color.
okay, but it's not in the real, the numbers, the neurons there are not representing place in space. It's
The what?
It's only a function.
Again, what was the question?
Okay.
No, it's okay.
It's only a function of this XYZ. It's not a real representation in space, this data.
You can think of it as yes, right? Because you can because you can query it in each point.
You can query at each point, but
Yeah, and this is exactly what we see in the thing that I showed you, right? Sorry. Oh. You can query the density in each point and take some level set of the density. And unfortunately, this is how it looks here. Okay, and this is why the density for nerf is not working. Yes.
So you're just thresholding the sigma values so you get that
Yes.
one there.
Yes, and again, it's done in 3D.
It would be more precise to say that the density is regulated only across like ray-wise. And here you look like a global threshold on the density, and it's not regulated like that. It's regulated to be ray-wise because the loss is ray-wise.
Okay,
So
so
you're not guaranteed that there is like a threshold which is like global and not ray-wise that you see the peak.
I think what you're claiming is exactly one of the problem because you don't have regularization of the density. I want to repeat what I said before. The density is only based on position. If you think of geometry, you cannot have like geometry that is depending on the view direction. Only the color is depending on the view direction, right? But eventually these two parts are just separate. Like you have, I don't know if you saw that from Merav, but eventually the structure of nerve, you have XYZ as output, and then a few layers of neural network of like linear layers, and then output is the density, and then you continue to have, and then you also input the view direction, and then you have another few layers, and then the output is RGB. So you have that separated. When you query, it is true that you render an image and you query, and the loss is supervised on something that is view dependent, but the density is restricted. And because of this thing that we will see later, is that we don't have this perfect disentanglement between the appearance and the geometry, we have this reliance, and basically the appearance, the color, kind of like compensate over the geometry, right? So think of like this area. It can just like color this area as white, and in the rendered image, it will be perfect, but the geometry will not be reliable. So this is something that we want to fix. Okay, so NERF introduced a way of doing differential volume rendering, and we're gonna try another approach that is called differential surface rendering. I'm sorry for this. I don't know how to. I don't know. It's not really bothering, right? Okay. So what's the highlight idea, the general idea behind differential surface rendering? We're still, as before, gonna have our camera parameters, and we're gonna represent the geometry explicitly, like we're gonna represent the geometry as a surface, okay? And then, in order to render an image, we're gonna shoot a ray, as before, find the intersection of the surface. We're gonna go through all these details, just like this is in high level. And then in this point, we're gonna query the appearance at this point that we intersect with the surface, and this will be our rendered pixel. Okay, let's dive maybe a bit more into details, but in general, the paper that suggested this idea, and it's suggesting an approach that is called implicit differential renderer, that it's called IDL, that is given some a neural representation of the geometry and a neural representation of the appearance and the ground truth camera parameters. We want to define some differentiable surface renderer that will predict us the rendered image. And like as before, as we did for NERF, the ground truth image will come from the input image that was really captured using these camera parameters in real life. And we're going to use the rendering loss in order to reconstruct all this like neural geometry, neural appearance that we want to learn. Okay. Let's maybe go into the details and go over that, and it will be more clear. So here you're gonna see what I kind of just like plotted here, but a bit more, explicitly in the face. So the neural geometry is gonna represent using implicit neural representation, and specifically the function that we want to approximate and represent will be a sign distant function. I maybe briefly started at the beginning. You're gonna have this. You can see this 2D example here. So this is the contour of like 2D sign distant function. This level set describe like positive distance to the surface. This is the 0 level set of the surface of the function. These are negative. So for each point, it predicts the sign distant function to the surface, and in that way we can represent the surface implicitly as all the points which the function gonna predict 0 on them. Okay, so I don't know if Rav told you, but given this implicit function, any implicit function, doesn't matter how it's represented, there are methods that can extract the level set, and this is basically how I showed you before, so the level set of the density as well. Okay, so our geometry is gonna represent it as a surface implicitly using this fully connected neural network that gets its input, x, y, z coordinates, and output one scalar, which is gonna be the sign distant function to the surface. Any questions? Okay, so as I said before, we want to render this surface somehow. What we're gonna do, we're gonna have an input, like currently some camera parameters that we have. We want to render a specific pixel. Once I'm defining how I render one specific pixel, it is like just like applicable for all the camera, for any camera that I'm giving you, or any pixel of this camera. So we shoot a ray through this pixel, and we want to find the first intersection of this ray with the surface. And we're gonna use that with something that is well known from computer graphics. It's not new. It's called an algorithm that is called sphere tracing. And this is also one of the ideas of one of the reason why we're gonna use a sine distance function. And let's go over the illustration here. Let's start. We're starting from the point that is on the camera, right? The P, and we want to walk through like doing ray tracing, trace on the ray, according to the sine distance function. So in this point, we can query the sine distance function to the surface, and it's gonna give us this sphere. And we know that if we're gonna approach, like we're gonna trace in the distance of the sine distance of the radius of the sphere, there's no way we're gonna cross the surface, right? Because we know this is the sine distance function to the surface. So we're gonna trace until this point, and now again, we're gonna query the sine distance function over this point, and again, we're gonna trace using the spheres until eventually we're gonna reach the intersection point. Okay, is this clear? So in that way, we get the intersection point of the surface, and think of like compared to now, so when we needed to sample points along the right, now we just like have one point, which is the most important point that we want to render.
But you can't generate a sphere that doesn't intersect the line, the surface twice, and then reach the point.
No, because for each, it's like it's just like one function, right? It's gonna give you the closest point. Even if you have like two things that are close, it's gonna give you the sine distance function to the closest surface, because this is the definition of a sine distance function. Okay? Yes.
I was gonna ask, how is that done explicitly?
What?
How is that done explicitly?
What do you mean?
So if you have a sine distance function that just tells you if you query at a point if it's positive, negative, or zero. So you have to query points all on the sphere, right?
So you only query, so think of like you start from the outside anytime, you won't be inside it at all, right? So if you start from the inside, from the outside, you only query points that are along the ray, right? So you start from this point, you don't need to query the points on the sphere, you just need to query this point, and the sine distance function will give you the radius for the sphere.
Oh, because it tells you the distance to the zero.
Exactly. Yes.
I don't understand why, you do this still in order to find the intersection point.
How can you find the intersection?
Just checking, putting the array and checking when it's there is line.
It's another way of, eventually you need to do like root finding, right? It's another way. This is much more effective. If you can query this along the ray until like, I don't know how many points, but eventually you want it to do as most efficient as you can. And this is like the most efficient way that you can, because you have the amount of like sine distance function, right? If you just like query points, okay, now you need to maybe query all these points here, and it's redundant, right?
You assume you already have the sine distance function?
Yeah, so so think like in compared to now when I told you that you have like random initialization, you can initialize this part as having like initialization of sine distance function for a sphere, and in that way you have like you're starting from a correct, like you're starting from a sine distance function, but it's not really represented with geometry. It's just like a sphere or whatever. Okay, wait. I'm always doing this mistake. Okay, I'm continuing.
But in the distance map that you have,
Yes.
this map is actually to the nearest
Yeah, to the closest point on the surface. Exactly.
of the surface.
Yes.
However, when you're taking this angle,
This is exactly why you cannot do this in one step, right? This is why you're going through, okay, what is promised for you when you're doing the steps, right? That you're not gonna cross the surface. And you're relying on this, and then eventually you're gonna converge and you're gonna reach.
Okay.
Now, the distance of each arc. This is
Yes.
what you're doing.
Yes, exactly. Continuing, okay? Okay, great. We found the intersection point, but now we need to render this point. If you're looking, I don't know, and the stuff here, eventually you don't care about what happens before. You just want to, if you want to render this chord, you're just gonna want to find this intersection and find its color. And for that, we're gonna have another small network that we'll call the neural renderer. It's, again, as I kind of like described you here, it's also what's happening in NERF. You have this geometry representation and this part that is like the color and the appearance that is represented. So in order to inspect the color of this position, we need to input. So again, think of it as like another function where the input for this is, first of all, the x, y, z coordinates, because we need to query this point, what is its color. We talked about like the importance of view-dependent effect, and we can see that here in this 2D illustration. If you have these two surfaces and you're gonna query the same point, the same intersection points from two different angles, you don't expect it to have the same values, right? Everything that you have in this world is reflective. I don't know, this board or whatever. If you're gonna change your view, the color is gonna change. It's also evident here, right? This is the same intersection point. If you're gonna see it from one camera, from one view, it's gonna be different than if you see it from this view, because this surface is gonna reflect it differently depending on the view that you're looking. So we want to model this view-dependent effect color, and same as in NERF, we're gonna do that we're gonna do that by inputting another variable to this function and condition this the RGB function on the view direction. Okay. However, it's not enough for us, and this is something that kind of relates to what you talked about and the geometry. And what we want to have is we want to have a perfect disentanglement of the geometry and the appearance. We don't want that the appearance model will kind of compensate over geometry artifacts. And a way to do that is to kind of like guarantee that we want to maybe able to render different geometry with the same renderer, right? If we can take another geometry and render it with an appearance model that is different, like not of this, that is like not for this scene, it's gonna give us the promise that we have a perfect disentanglement between the appearance and the geometry model. Okay, and then it's gonna give us the question of, okay, what kind of inputs we want to have to the neural renderer to have in order to generalize across the geometry. And what we're gonna use is gonna use the normal. The normal is just like the direction of the surface. I don't know, here it's like orthogonal or whatever. And I don't know if you cover this concept with the Yariv, but it's just like the normal direction from the surface to the outside. Okay, and another way to think of the normal is kind of like describing the local geometry around the intersection point. Okay, so we want to pass or condition to the appearance model a local geometry information in order to render it perfectly. And maybe to better demonstrate it, we're gonna call it maybe geometry dependent color. It's a bit more hard concept to maybe understand than the view direction, which is more visible, but let's consider this 2D example here again. Think of, you have this surface and geometry, and if you don't condition on the normal, once your surface is gonna change, the normal will change, you can predict the same color, right? So it doesn't matter what is the input of the normal that I'm giving you, you're gonna predict the same color, but you don't want to have this ambiguity of the normal. You want to render according to the correct normal. meaning according to the correct geometry. So,
Geometry, it's upon the maximal and distance map.
Again?
This is actually, it's the normal.
again, what?
The maximal value or the value of the distance map in a certain location,
Yes.
it's actually the normal to the nearest place in the contour.
Yeah, it's another way, but eventually it's, right, it will be, the normal will be the gradient of the sine distance function at this point. Don't know, eventually, right? So again, it's just like another way to think of it. I like to think of it as like, capturing the local geometry around the intersection point. Okay. This is our next addition, which is going to be the normal. We're going to see the effect of the normal later on in the ablation that I will show you, and maybe it will be more clear how it really affects this disentanglement and this ambiguity that we don't want to have. Okay. So, and one last thing. I think you talked with Merav about local illumination and global illumination, right? Local illumination is like the first appearance that is captured. But when you talk about global illumination, like secondary light effects, if you have self-reflectance or shadowing, so this is something that is not captured only by like local geometry property. And we kind of want to describe some, option for the renderer to model secondary lighting effects. And we do so by adding another global feature, which is the input of the geometry. So think like we're allowing the geometry network to kind of like pass to the renderer some global feature that is describing more global effects over the geometry. And we pass it also again to the renderer. Again, maybe it will be more clear in a few slides when we're going to see an ablation of how each thing of like this really affects on the constructed geometry.
The X hat is the surface personalization.
What?
The X hat input is the surface.
Is the surface intersection. Yeah, this one. And the normal also is like the normal from the intersection point. Yes, sorry.
Do you mind saying again what is the purpose of the first network?
Of the what?
The first network.
Yeah, the first network represents for you the surface, right? It's have a sine some function, so it's zero level set all the function on the output that is having zero in space in R3 in XYZ, gonna give you this surface exactly.
So what is the output of this network?
One scalar, an SPF.
The input is it the same with what is the input to the neural geometry?
This the XYZ, like the position.
Okay.
Okay, another question? We have all this framework and we want to train it, so we have parameters for the MLP above and for the neural renderer. And because all this process is going to be differentiable, we're going to use the same rendering loss as we introduced with the NERF and compare the parameters pixel with the rendered pixel.
You have some concern about the number of examples?
You need to have some good coverage. And once again, when you have like more regularization of surface, it maybe will be easier, but if you have like 5 input images, you're not gonna model it correctly. You need some good coverage. I think most of the works for NERF, they're using something between 50 and 100 cameras, something like that. But yes, it's pretty much, and if it's like big scenes, it can be even 1,000. So it's ridiculous. You need some good coverage. Another last important particle aspect for this framework is that I think Merav mentioned the position encoding. Position encoding is something that they introduced in NERF, and the idea is just like, so maybe I lied to you before, and the input is not XYZ, it's XYZ, but plus the position and encoding of that. So the idea behind position and encoding is that you want to add to the network the high frequencies of it. So you model high frequencies by just like really inputting high frequencies into the network as an input. So sinus and cosine of different levels of frequencies. And this will gonna give you all the details because I know you thought that, I know that Merav mentioned that neural networks kind of sometimes have struggled to learn high frequencies in early steps. You can see here in the ablation, if you train for surface reconstruction, this there we're going to see the example also later, without positional encoding. So just like a simple MLP where the input is XYZ, it will take you 5,000 epochs and you're still going to reach kind of like smoothie surface, while with positional encoding, you can capture all the fine details in only 2,000 iterations. So this is one of the nice contributions of NERF, and everybody that are using that doing neural rendering today basically use this position encoding in order to learn this. Okay, so let's see some results. So from the left, you see this is like a set of the input images. You don't have only 4 images. You're gonna have again around the 30, 40, something like that. And from the right here, you can see both the rendering of this thing and the extracted surface of the zero level set of the neural geometry plot. So you can see it really capture the reflection effects and the nice geometry with the details. Okay. So if we examine some comparison method, so the thing that we can compare is like, first of all, it's COMAP. It's a classic method that based on multi-view reconstruction, and it's just gonna give you some dense, think of like dense point cloud, and it's not really a surface. This is why you're gonna have these missing parts, and it's not really modeling reflectance or the appearance correctly. So this is also why you have some missing parts. DVR is a previous work that you can think of. The main comparison to IDR is that it modeled the renderer only as a function of the position. It doesn't have either the view direction depending or the normal, and you can really see the effect of the geometry on the geometry with that, right? If you cannot model reflectance, you cannot model change in the geometry, you're going to compensate with the geometry over that, right? So think of you want to model this, reflectance area. So in order to really have a ball and represent the geometry, the appearance is a function of the view dependent, you're going to have this bump inside and you're going to query like different views from each part, right? So it's kind of like doing a trick in order to really model the appearance correctly. So this is what I actually wanted to talk with you about the ablation and the effect of each one of the inputs to the surface reconstruction. Okay, so first of all, if you look at the view dependent, again, as I told you before, because you cannot model the reflections and the specularity, the geometry kind of have this extraneous parts in order to simulate different viewing effect from different angles, right? So it doesn't have another way in order to match the ground truth images from multiple views otherwise. If you look at the normals, you really see the ambiguity, right? Because you can have this degrees of freedom that your normal is going to change, your surface is going to change differently, and it's not depending on the local geometry. It doesn't have this localization of having a nice smooth surface, and you're gonna have this noisy as you can see, when you don't have the normal as input to the renderer. And the last thing, which I found really nice, is if you omit the global feature that I told you that we want to add for the secondary illumination effect, you cannot capture like, I don't know, the chin that's supposed to have some kind of like a shadow, right? So you're gonna have this extra chin in order to, which is gonna be like, I don't know, painted with dark in order to kind of like simulate this shading. Yes, no question?
What is it?
That is like the globe. We had like a global feature that is like another output from the neural geometry, and it's input to the renderer. So it's allowing kind of like to the renderer to represent the global effects. Like
Some type of diffuse illumination, and
what?
it's like diffuse lighting, light that come from everywhere. It's representing.
Yeah. It can also like, but I think like we give the network another option to represent this secondary lighting. Yes.
When you say the result is a geometry, you mean the distance map, right?
Again, what?
When you say that the result is a geometry, you mean the distance map actually?
The sin distance function?
Yes, the distance function. Is that what you give us a geometry? Like, what does it give us a result in terms of geometry?
So as a result, you're gonna have a function that is trained to render and reconstruct to render the scene, right? And then you can take only the first part, which is the neural geometry, right? Which is the distance map, the sin distance function, and you can query its zero level set, the surface. And this is what we see here. This is the zero level set of the neural geometry part.
And it seems to detect a lot of very fine details. If you try to do like derivatives on this geometry, say like go from like get the derivative of the normal along the way.
Yeah.
Do you get like a lot of huge jumps, or do you get something smooth?
You're gonna get something smooth, and this is because that you are kind of like regularizing for a sin distance function, which I think also something that Merav mentioned, because then it has like a normal, the gradient is with magnitude of 1. So because you have something that is, I don't know, well defined in terms of a surface, like a sin distance function, you're gonna have a smooth function everywhere. Yeah. Even though you're gonna have details, the details you're gonna get from the high frequencies, but it's not meaning that, doesn't mean that the function is noisy. Yes.
What is the loss?
So the loss is everywhere is the same thing. Is the rendering loss? Is like the rendered image is the simulated rendered representation. We want it to match to the given input image. And the only thing that we change here is the architecture of the network. Okay.
But how you use the N? I mean,
What?
so the N, how do you use the N in the loss?
You don't use them in the loss. You use it in the predicted rendered color, right? It's like what you input to the network. Just that. Another thing that I talked about, I mentioned that if we're gonna have a perfect disentanglement of the geometry and the appearance, we'll be able to, if we're gonna be able to switch between the renderer and the geometry and kind of like render different geometry with the same render part, this will gonna give us the perfect disentanglement between the geometry and appearance. And it can be seen here. So think like each one of these, each one of the scenes were trained separately, completely separately. And right, I told you we have like two parts, the neural geometry parts and the neural renderer parts. And what we're gonna do now is just like switch between these networks. So we want to render the first geometry using the rendering network of the second scene. Okay, and this is what we're gonna get here. So we see that this the architecture that we have, the fact that we model it using the normal and the view direction, gonna give us this perfect disentanglement between the two between the two parts as we want. And really, if we not gonna input the normal, as I told you before, we're not gonna condition it as an input, we get noisy geometry, and we know that the appearance model is gonna rely on the geometry, and we don't have this type of disentanglement, and we cannot do this switching. Okay. I think we're gonna do a short break, and then we're gonna continue. Okay, so what is the time now? I want to maybe, because some of you approached me in the break, and I know it's like a mind shift, and until now in the course you've been used to like having input, bunch of images, a batch of images, or whatever, and output, I don't know, classification, segmentation, whatsoever. So this is not the regular paradigm when you have like input set of images, output the representation of a convolution network. It's a different way, and because it is a different way, because the really idea is to simulate the real rendering that is happening in computer graphics, right? So I'm just gonna want to maybe go over the high-level paradigm again. So the idea is that you have an image and you have a set of cameras, and you want to have some scene representation that when you render it from these cameras, you're gonna get the input image that are corresponding to the camera. The really idea is to simulate the rendering in order to reconstruct the scene. Once for each one of the views, for each views that you have for the cameras, you're gonna render and get the ground truth image. It means that you reconstructed the scene that you have in hand. Okay. Do you have any other question on that? Maybe, and it's still not sitting right.
So that's rendering. It's like a classical rendering.
What?
What you just explained, you just did a classical rendering. Right?
I did,
Machine learning.
but and the machine learning it's entering is like how you represent the scene. There are two things about what the machine learning or the deep learning is. Okay, there is no machine learning here. This is something that I want to say. There is no machine learning. You don't like the only machine learning that you can think is like for machine learning you need to generalize across scene. Here you have one single scene. Each time you work on one scene that you want to construct. The maybe thing that you can think of like as machine learning is that you interpolate between the views, and you have the generalization of the surface that you're constructing.
So you have all the 3D image and you
Or
want.
the what?
You have the 3D image already. It's like your.
You don't have the 3D image. You have only 2D images.
Okay. You have 2D images.
You have 2D
and
images.
you want to reconstruct what?
And you want to reconstruct the 3D. And so the difference here is that, and what are the deep learning center? The 3D enters the deep network centers. They will be the one that we use in order to represent the scene. We're gonna render this thing. We're gonna make this process differentiable, and using that, we're gonna reconstruct the scene. Yes.
So what's the difference between the this network and this network?
Yeah, so let's maybe go over it. This is one of the things I want to go over now. Okay, so you would led me into what we want to discuss now. So I introduced you a way of doing surface rendering, and now introduce a way to do volume rendering. Both are way that you render your representation in a differentiable way, and you learn the scene by comparing the rendered image with the ground truth image. So let's go over the differences. So the first is in terms of the representation of the geometry, right? In surface rendering, we represented the geometry using an implicit neural surface. We presented as a function that has like x, y, z as input and assigned this function, and this is gonna give us a way to extract the surface. In volume rendering in MELF, we represent the geometry as volume density. They're just gonna give you for each point in space the amount of density. And we saw it has some, it can be like, it's not really reliable in presenting the geometry correctly. In order to render surface using surface rendering, you just need to find the intersection. In order to render using volume rendering, you need to sample points along the ray and approximate this integral approximation, like finding the expected color according to the samples that you have. So it also leads us to the next difference, where for surface rendering, when you backpop your rendering loss to the weights of the networks, you only have one example, which is the intersection point. And with NERF, you're gonna backpropagate along all these rays. So each one, because you have like an integral approximation that is relying and depending on each one of those points, the loss will gonna be differentiable according to each one of these points. So basically this difference, because there is something that I misled you before, and another thing that we needed to use in order to learn IDL is we needed object masks. So we didn't have an is input only the images. We also have an object tag that's going to give us where is the object and what is the background. And the reason we need to use that is because in surface rendering, our loss is going to be defining only on the points that intersect. And we cannot model the rendering of a point that is not intersecting the surface. Okay, and for that, we need to kind of like reason for only the point that are intersecting, and this is why we need a mask. And really, if we just learn IDL without having a mask, we can see that it has this extraneous thing that it grows because it cannot reason about the areas that are like it cannot differentiate between the between the background and the object. This is different in volume rendering because you can just like sample points along the array, and where the way that you can model background is that it's just like, you know, either this density is contribute 0, or it's just like, you know, put only in the last point some background color, and in that way you don't have this this difference between background point and object point. You can simply render and differentiate according to this each point that you have. So NERF doesn't need any additional input as masks in order to reason about background or foreground.
Where can you just intersect the floor in the case of the skull?
What if you have a wall? And how can you change whether it's a wall or like if you are outside or whatever, like this photo, you just like lie and then you intersecting, I don't know, very far away. It has some ambiguity and it's not well defined. And I think that the actually problem is that think of like a point that is almost intersecting, but it's not intersecting, right? You need to somehow you know, have gradients to the geometry according to that. For NERF, you're gonna have, because you're gonna have maybe when you're approaching the surface, you're gonna have like maybe a small density that you're accumulating. But for a surface, it's just like either you're intersecting or not intersecting. And this is gonna give us the like you need also this lack of ambiguity of like concept of almost intersecting in order to really you know, render it correctly. And so really the main limitation of volume rendering, as we saw, is that the geometry is not really reliable representing the scene. And if we take some threshold over the density, even though the rendering look perfect, the density is not well reconstructed of the surface. Okay, so our next thing that we want to ask, okay, how can we get best both world? How can we maybe combine these two concepts and I don't know, maybe we can do surface reconstruction and have accurate geometry, but won't need this use of additional signal as masks. Okay? And this is going to lead us to the next thing that we're going to do is we want to do surface reconstruction using volume rendering. Okay, so before we did surface reconstruction using surface rendering, and now because we have, as I told you, we have this concept of we want the ability to also reason about points at almost intersection. This is something that we can do with volume rendering. We just want to maybe change the geometry representation just to do surface reconstruction well better than what Nerf is doing. All right, so let's look at this 2D example here. This is our surface. Let's say we have some surface representation and we want to do volume rendering. How can we do volume rendering to the surface? Maybe this is related to what you said. We want to maybe find intersection. But in volume rendering, we simply query some points of the function along the ray. And the chances for us to find this, if we just like sample this point, the chances that we lie on the intersection point is merely zero. The probability for that is merely zero, because you think of like, I don't know, a delta function, and there's no way you're gonna hit it by just like randomly sample points along this ray. So the idea is to take the surface and not really represent it as a surface, meaning we want to maybe represent it as like a fuzzy surface or a soft surface and blur it a bit. And in that way, we can use volume rendering in order to render it. Okay, so this is the concept that we want to have in mind. So how are we gonna do that?
Could you not do that for surface rendering also?
What?
Could you not use that method for surface rendering also?
But for surface rendering, and you just need to surface the render the surface. It's things like we want another way. We gonna use another rendering method. In surface rendering, you find intersection. In volume rendering, you sample you sample points, you sample the density, and you accumulate the density along this ray. Okay, and the surface is very like a delta function, kind of like a density, and it's very hard to perceive and sample, and that is why we want to kind of like blur out the surface in order to render it. Okay, so how are we gonna do that? As before, we're gonna use a sign distance function to model the surface, right? As I told you, we have an MLP, a fully connected network, that's gonna represent as a function that's going from R3 from XYZ coordinates and output a scalar, which is gonna be the sign distance function to the surface. So as before, this is our surface. This is the zero level set of this function. This depicts like negative level sets, like the negative distance to the surface. And this is going to be our positive surface, positive distance to the surface. And we're going to use some function to model the density as a transformation from the sign distance function to a density. So eventually we want to have a density. In another way you can think of it is that instead of modeling the density of Nerf as, I don't know, a general MLP, a general function, we're gonna have some prior knowledge of it, and we wanted to have some underlying surface underneath the density. We're gonna choose a specific set of families of density that we're gonna optimize for. So, okay, specifically, what is the formula, what is the transformation that we're gonna use? As before, you see here in the illustration, you have your geometry represented with sine distance function. Again, this level set's kind of trying to illustrate the level set of the surface. And we're gonna use a Laplace cumulative distribution function. It's just like a function. You can also think of a sigmoid that transform new points to be between 0 and 1. Another way to think of this transformation is that it's taking a sine distance function to be indicator function, right? So think of, so what it's gonna be if I'm positive, if I'm like positive distance to the surface, I'm gonna have 0 density, okay? And when I'm reaching to the surface, the density is gonna increase, and eventually inside the surface, I'm gonna be inside, I'm gonna indicate 1, okay? So, and we multiply this indicator function with alpha, so we're gonna have like alpha density everywhere. So again, let's go over it. I have a sine distance function to describe for each point in space whether I'm outside or inside the surface. So when I'm outside of the surface, I have positive distance. I'm gonna have 0 density, which is clear. And when I'm approaching the surface, inside of the surface for the negative, I'm gonna have a very high alpha density. Okay. There is another parameter here, which is called beta, and it's pretty much what it's going to give us. It's how much fuzzy around the surface we want to be. So like I told you, I showed you before, like the green thing is, I don't know how much I want to accumulate some density when I'm approaching to the surface. And think of that way, we make some problem that is a classification, whether I'm inside or outside, I'm intersecting or I'm not intersecting, that I can almost intersect the surface and I still gonna have gradients to the geometry. Yeah. Okay, some questions? Maybe it was a bit, all good? Okay, so again, recall that for NERF, we just use density as a general purpose MLP, and here we want to use a certain families of density which have sine distance function underneath. So it's gonna give us the regularization for the geometry as we told as we need. So wait, maybe I want to. So I didn't give you I didn't give maybe another slide of the general framework, but from here, we're just gonna train it like a regular NERF, right? As I told you before, the same paradigm. You're gonna have input cameras and their corresponding images that were captured in real life. And what we want to do is we want to do volume rendering as we did for NERF, but the density we're gonna use is this density. So we train a NERF, and we just replace the parameterization of density with this specific density, and we're gonna render the same way. That's it. Yes.
The Laplace working on the density and so
What again?
the Laplace
Yes.
is working on the density.
Is on the sine distance function. Is
This
yes. Okay. This one. I heard density. Sorry. Yes.
no, this
Okay.
and what that you're actually doing is kind of cut off of the large values.
Exactly.
They emphasize the location that are nearest to the contour.
Yes. Exactly.
Want to stretch it in
Yes. Exactly.
to emphasize where exactly the location.
Yes.
This is the intuition.
And in that way, you can think that, okay, I don't need object mask anymore because I don't have this difference between the background and foreground. Everything if I don't have nothing there, I just like accumulate 0, place some color in the background, and that's it. Or I'm almost intersecting, I still can accumulate some density and have this region, and then I solve the problem. I don't need masks, but I also regularize density that I had for nerve, and I can extract a well-defined surface out of this representation. So another way you can think of it is just like adding some regularization for nerve representation of the density to model it better. Any more questions? Okay, so let's look at the results. Something that I didn't mention, and one of you asked in the break, that all these results are like, this is from a real data set. This is a data set of some objects that are placed in some studio and captured with some cameras. So it's not synthetic. And I think what you can see here is that you see the rendering of both in the method of VolSDF, you saw it before, and nerve, right? Kind of like look reasonably the same. But if you look at the geometry that you extracted either from the density or from the zero level set of the sinus and function, the distance map, you're gonna see the difference of much more well-defined surface and detailed one. And you don't need any mask for this.
What about compared to the method from before?
Nice you asked, it's right here. So again, you can see that you're gonna have the same details, the reconstruction is basically the same, but here you need this object mask as additional input to your problem. And here, you don't need it. So sometimes you do reconstruct some of the table, but it doesn't really matter. And again, compared to nerve, you see that the geometry is really, really noisy. And compared to Colmap, which is like the classic method, you still can see some parts that are missing and maybe a bit also kind of like artifacts and noisy. So this data set, as I told you, is it's called the TU. It's a data set of some objects that are lying in the room. But what if we want to model maybe a more complex background of objects in the output, right? So this is another thing that and there is another data set that is called blended MVS. It's also of real objects that are captured in the outside, and there is a follow-up paper from NERF that is called NERF++ that suggested to model the background as a more complex function. We won't get into the details, but we can do the same thing as we did here, and just use our density parameterization of having an underlying sinus function and reconstruct the foreground object out of these scenes, even though the background is much more complex, just like line on the table.
How do you get the ground truth of the geometry?
So the ground truth you can think of like the ground truth is not the geometry. The ground truth is this is not the ground truth. You see the line here. The ground truth is just like the no, sorry, wait, no, the ground truth is given using some classical method that you have. I forgot about that. Sorry. Yes.
That method works really well.
Yeah, so this is no, it's not like another method. It's just like, so I don't want to get into the details. So it's like semi-synthetic data, right? And they took like some object, and then they re-render it in real life. So so it's not really real data, and this is why you have the ground truth. But I don't want to confuse it. Yes, I forgot. Okay, so another thing, because we saw that in IDR as well, we have the same methodology of the renderer as the input. So we have these properties of doing this disentanglement. So on the diagonal is like you can think of like each one of the scene is trained separately, and it's rendered using its original one. And in each one, we have this mix and match of, using this geometry, this sigma, like the density, using the rendering of this model. So you can see that we still can switch between and render different geometry with the same, with the different render, and have this generalization that kind of like state that our geometry is really well reconstructed and is not depending on the view, on the appearance model. One last thing that I wanted to kind of like mention in the end is why do we care about surface reconstruction, right? Why we have novel view synthesis, isn't that enough? So maybe some other application that can motivate for you. So for me, I don't know, I like to watch this circle surface extraction and it's nicer for me that I think than just like view as a novel view synthesis of the scene. But there are much more applications once you have a well-defined surface that is extracted. One of them is relighting. Given the surface, you can relight the scene whenever you want. And another thing is that you can do appearance editing, right? Since you have the surface itself explicitly, once you have this, once you train it and you have and you extract the surface, you can have in hand the surface explicitly in hand. You can, I don't know, modify it with appearance modeling and all this type, all this stuff that I showed you. And another thing that is becoming more popular recently is that you can do real-time rendering. So I don't know how much of you are playing computer games or whatever, but you talked with Merav about the difference between rasterization and ray tracing. And when you do ray tracing, again, in order to render something that some geometry, you need to trace, and it can be a long time. Also, volume rendering can be very, very tedious. Once you have a surface, you can use rasterization, which is much more faster, and in that way you can do real-time rendering. And this it's just like you do a novel view synthesis on the computer. You just like toggle the scene that you reconstructed, and this is something that is possible only using surface reconstruction. And volume rendering can take, I don't know, few minutes just to render one single image. So again, I mentioned the computer games because all the computer games are based on rasterization, but just for you to know.
Are there any video games that have used this?
I don't know. I saw just some people on Twitter, but VR is approaching as well, so maybe that as well. Okay, so let's summarize. I know that was pretty much a lot, and again, it's a different paradigm. It's a different maybe mind shift, but let's just like go over the takeaway messages that I want you to come from this this presentation, this lecture, and Merav's lectures. So the first is that we saw that using NeRF in order to extract geometry, we're not gonna get really reliable geometry of the scene, and it's not smooth and it contains some noisy artifacts. We can use surface rendering, and it have very highly accurate 3D reconstruction, but it depends on the object masks. However, if we unify these two approaches, we can do surface reconstruction using volume rendering approach. And even though the results are pretty much convincing and nice, there are some limitations to it. The first that is true also for both NeRF and IDL and and VolSDF and pretty much all of the methods that you saw is that it's each one of the scene is trained separately per scene. It's not like, again, paradigm that you're used to. You have a big deep neural network that train on a bunch of I don't know, a data set, and it can classify cats and dogs, and then now given a cat outside of the blue, you can classify whether it's a cat or a dog. So here you need to train, and it sometimes can take a long time, like each scene can take around 6 hours just to train for it. So it's pretty tedious. Again, as I told you before, doing volume rendering and also both surface rendering is pretty much computationally expensive, and to render one single image using NeRF or the other method can take a few minutes. And some limitation that is more related to the representation that we chose, which is time distance function, is that it assumes that you have a fully opaque surface. So using SDF, you cannot model some, I don't know, if you think about the hair, it's not really a surface. It doesn't something that has like boundaries that is well defined, or a smoke or stuff like that. So time distance function have to, like, in order to model some object as a time distance function, you need to have well-defined inside and outside of the state. So if you can think like a paper or some really, really thin stroke, this is something that it's very, very hard to represent using a time distance function. And this is something that, again, that is maybe more easy to do with the density, but you know, you need to do this trade-off of whether you want a very nice and all the thin structure or a well-defined surface. So again, this is just like in a nutshell. NeRF was like 4 years ago, and since then this field is pretty much exploded. And all the computer graphics people really loved it. So there are many follow-up works that did other applications. Some of them are the 3D generative models, like if you want to render some 3D, given a text input. Another thing is to model dynamic scenes, right? So you don't have everything that you saw before was like static objects, and nothing is moving. Whether maybe you want to maybe reconstruct some walking person or jumping dog or whatever. And another thing is that we assume that we have the cameras as input, and maybe you don't have the camera, you just have the input images without their corresponding camera, and you want to also optimize for the camera. This is also an important task. Another thing that is nice that I think I showed you just like the separation between the geometry and the appearance model, but also the appearance model has these two properties of material itself and the lighting is in the room. So there are many works that try to kind of like decompose that as well. And really, there's so many more. I cannot even start with it. So I kind of like plotted here some of the survey or blogs that are mentioning if you're interested in this topic. I really welcome you to start with this kind of like blog and paper posts. And if you need more reference, please feel free to approach and I can direct you. And that's it for now. If you have any questions, feel free.